Section: Introduction. In this section, we delve into the fascinating world of large language models, LLMs, and their internal dynamics. Our journey begins with an acknowledgement of the impressive feats achieved by these models, which have been primarily assessed through their external behaviors, such as task performance and response accuracy. However, we believe it's equally important to understand what goes on under the hood, especially as these models find their way into various real-world applications. Despite the significance, the exploration of ILM's internal mechanisms has been somewhat limited. Our investigation led us to a surprising discovery within the internal representations of LLMs. When we looked into the hidden states of these models, we found instances of certain activations that were astonishingly large, more than 4 orders of magnitude larger than the median and sometimes exceeding absolute values of 15,000, even in models like Llama 2 to 70B that incorporate normalization layers. These massive activations are not just large, they're also incredibly rare, often appearing fewer than 10 times among tens of millions of activations. Given their significant size difference compared to other activations, we've aptly named them massive activations. Our research shows that these are not isolated incidents but occur across a wide variety of LLMs, regardless of their size or family. We took a closer look at where these massive activations are situated within the LLMs and found that their emergence is quite sudden, appearing abruptly after a single layer of computation and then diminishing in the final layers. Interestingly, these activations are not tied to specific inputs but occur in a small number of feature dimensions, often associated with the starting word token and delimiter tokens. It's crucial to note that massive activations are distinct from outlier features previously identified in LLMs. We discovered that they act as fixed but essential bias terms within the models, similar to the bias term in a linear layer equation. For example, in Llama 2 to 7B, nullifying just 4 of these massive activations led to a dramatic drop in model performance, underscoring their critical role. However, adjusting them to their mean values did not adversely affect the model, suggesting they function as simple constant biases. Our analysis further reveals that after the initial layers, LLMs repurpose tokens associated with massive activations to store these crucial biases. Intriguingly, we found a strong connection between massive activations and self-attention mechanisms, with massive activations drawing attention to their associated tokens. This extends the concept of attention sinks and provides a deeper understanding of how attention concentration patterns develop in LLMs. We hypothesize that LLMs attempt to learn implicit bias components in self-attention through massive activations during their pre-training phase. To test this, we experimented with augmenting self-attention with additional key and value embeddings explicitly designed as biases. Remarkably, this approach eliminated the need for LLMs to learn massive activations. Our observations of massive activations are not limited to LLMs. We also found them in vision transformers, VITs, albeit less frequently. Like in LLMs, these activations in VITs act as fixed biases and are found at fixed feature dimensions but vary across patch tokens. This similarity led us to draw connections between massive activations and the concept of register tokens in VITs, suggesting an alternative interpretation of their function as fixed biases rather than aggregators of global image information. In summary, our exploration into the internal workings of LLMs has unveiled the critical role of massive activations and their implications for model behavior and performance. This insight not only enriches our understanding of LLMs but also opens new avenues for optimizing and designing future models. Section Summary. In this section, we investigate a surprising discovery in large language models, LLMs, where certain activations within the models exhibit significantly larger magnitudes, termed as massive activations. These massive activations, despite being rare and few in number, play a crucial role as fixed bias terms in LLMs, influencing model performance and attention mechanisms. We find that these massive activations are not unique to specific LLM models but are observed across various LLMs, showcasing their importance in understanding the internal mechanisms of these models. Section: Which layers? In this section, we explore which layers of certain language models show the most significant activations, meaning the points where the model's output is most intense. We looked at the output from each layer of 3 different models, Llama 2 to 7B, 13B, and PHI-2, and averaged the results over 100 sequences. Our findings show that the most intense activations tend to occur at the same spot across many of the middle layers of these models. Specifically, these intense activations start appearing in the early layers, remain fairly constant through the middle layers, and then start to decrease in the last few layers. For example, in the Llama 2 to 7B model, these activations first show up in layer 2 and stay consistent up to layer 30. Interestingly, in both the Llama 2 to 7B and 13B models, these activations appear suddenly rather than building up gradually, suggesting they're caused by a different mechanism than we might expect. Next, we delve into where within the model's hidden states these intense activations occur, focusing on their feature and sequence dimensions. By examining a middle layer, we found that in the Llama 2 to 7B model, 2 specific feature dimensions show these activations. As for the sequence dimensions, these activations are linked to the first word token and the token representing either a period or a new line in the sequence. This pattern holds true even in longer sequences, with up to 4 intense activations occurring when these specific tokens are present. In the Llama 2 to 13B model, the intense activations are consistently found in 2 feature dimensions and are always associated with the starting token of the sequence. Another model, Mixtral 8x7b, shows a similar pattern but includes additional tokens like and of as points of intense activation. Summarizing our findings across various models, we noticed that intense activations are typically found in very few feature dimensions. When it comes to sequence dimensions, we categorize the models based on where these activations occur. Some models show them only at the starting token, others at the starting token and the first strong delimiter, and a third group shows them at the starting token, various delimiters, and certain low semantic words. Lastly, we differentiate these intense activations from outlier features, another phenomenon observed in language models. While both involve high activation magnitudes, intense activations are scalar values linked to specific tokens, whereas outlier features are vectors affecting all tokens. Moreover, intense activations occur at far fewer tokens compared to outlier features. In our analysis of Llama 2 to 7B and 13B models, we identified several outlier features but found that none of them matched the feature dimensions of the intense activations, highlighting a clear distinction between the two phenomena. Section Summary. In this section, we identify layers in LLMs where massive activations occur, showing that these activations remain constant across most intermediate layers and emerge rapidly in specific layers like 2 and 4. We also determine the feature and sequence dimensions of these massive activations in models like Llama 2 to 7B, 13B, and Mixtral 8x7b, finding consistent patterns such as activations at starting tokens and specific word tokens. Additionally, we differentiate massive activations from outlier features, highlighting that massive activations are scalar values at few tokens, distinct from outlier features which are vectors across all tokens and layers. Section. Massive activations act as biases in LLMs. In this section, we explore the significant role that massive activations play within large language models, LLMs. Initially, we were curious about whether these massive activations were crucial for the model's internal computations or if they were merely superfluous. To get a clearer understanding, we decided to actively manipulate these massive activations and observe how such changes impact the LLM's behavior. We began by examining the variability of these massive activations across different input sequences. In addition to focusing on massive activations, we also looked at 3 other types of activations based on their average sizes, specifically the top 1%, top 10%, and the median within the hidden states. By analyzing 100 sequences in 2 versions of the Llama model, we noticed that the variability of massive activations was relatively small compared to their average values, especially when compared to other types of activations. To delve deeper, we modified the ILM's inference process by adjusting the massive activations at a specific layer. For any hidden state that showed massive activations, we manually set these activations to fixed values. After making these adjustments, we continued with the normal computation process in the subsequent layers. We conducted this experiment on both the Llama 2-7B and 13B models and assessed the impact on various benchmarks, including perplexity on datasets like Wikitext, C4, and PG19, and mean zero-shot accuracy on tasks such as BoolQ, PIQA, Wino Grande, ArcEasy, and ArcChallenge. One of our interventions involved setting the massive activations to 0 at the point they first appeared within the hidden states. Surprisingly, this led to a significant drop in the model's performance, with a notable increase in perplexity. For comparison, we also set an equal number of activations, those with average magnitudes close to the median, to 0 and observed no performance degradation. This experiment highlighted the indispensable role of massive activations in the internal workings of LLMs. In another experiment, we adjusted the massive activations to their empirical mean values, calculated over 100 sequences. This intervention resulted in minimal changes in both perplexity and zero-shot accuracy, suggesting that the values of massive activations are constant and not dependent on the input, thus acting similarly to bias terms. To summarize, our findings indicate that massive activations function as crucial, fixed biases within LLMs, significantly influencing their computational processes. Moving on to the effects on attention, we investigated how massive activations influence the self-attention mechanism in LLMs. We observed a clear shift in attention patterns before and after the emergence of massive activations. Specifically, in layers following the appearance of massive activations, attention was predominantly focused on the tokens associated with these activations. This pattern was consistent across different LLMs, including Llama 2-7B, Llama 2-13B, and PHI-2, when processing the same input. Our analysis showed that attention logits, which are calculated before the softmax operation and determine the distribution of attention, were mostly negative except when associated with tokens having massive activations, where they turned slightly positive. This means that during the softmax calculation, these tokens with massive activations attract the majority of the attention probability. Interestingly, while previous research highlighted that LLMs tend to heavily focus on the starting token, our findings suggest that LLMs also allocate significant attention to other tokens linked with massive activations. This reveals a deeper reason behind the emergence of these attention concentration patterns, underscoring the importance of massive activations in shaping the behavior of LLMs. Section Summary. In this section, we delve deeper into large language models, LLMs, to investigate the role of massive activations within them. By modifying these massive activations and observing the impact on model performance, we find that they act as crucial fixed biases in LLMs, significantly affecting internal computations. Additionally, we discover that attention in LLMs is concentrated on tokens associated with massive activations, influencing the distribution of attention logit values and shedding light on the internal mechanism of LLMs. Section. Massive activations impose implicit attention biases. In this section, we explore how large language models, LLMs, use significant activations to implicitly influence the focus of self-attention mechanisms. Specifically, we examine the roles of the attention layer normalization and the projections for queries, keys, and values, Q, K, V. In LLMs, input features are first normalized and then transformed into these Q, K, V states. This approach, which was introduced with GPT-2, is now a common practice in many modern LLMs. Our observations, particularly from analyzing the Llama 2-7B model, reveal that features of certain tokens, which undergo massive activations, stand out significantly from the rest right after normalization. These tokens then show less variation in their subsequent Q, K, V states. We suggest that the attention layer normalization might be crucial in this phenomenon. Further, we dissect the output of the attention mechanism by focusing on tokens that receive a lot of attention due to massive activations. We break down the attention output for each token into two components, one that comes from the highly focused tokens and another from the rest. This analysis shows that the updates from the focused tokens act almost like a constant bias, even though they are not explicitly defined as such. This pattern remains consistent across different inputs, indicating a systematic way LLMs allocate attention to certain tokens, thereby introducing an implicit bias in the attention computation. Moving on, we experiment with introducing explicit attention biases to see if we can eliminate the need for massive activations. By adding extra learnable parameters to the attention mechanism, we find that models equipped with these explicit biases do not show the massive activations characteristic of standard models. This suggests that explicit attention biases can replace the need for LLMs to develop massive activations during pre-training. We also investigate whether vision transformers, VITs, exhibit similar massive activations. Unlike LLMs, VITs mix tokens globally and are not autoregressive. Our findings show that massive activations are present in some VIT models but not all. For instance, CLIP and DINOV2 models show few activations with significantly larger magnitudes, while MAY models do not. These activations in VITs act as fixed biases, crucial for the model's performance. Interestingly, when we modify these activations, the performance varies, highlighting their importance. Recently, the concept of register tokens was introduced to augment VITs, leading to smoother attention maps and improved performance. Our analysis of these models reveals that massive activations are stored within specific register tokens, suggesting that these registers serve a similar purpose to the explicit biases we experimented with in LLMs. By replacing register features with their mean values, we demonstrate that these tokens act as learned biases, confirming their role in enhancing model performance. To summarize, our findings highlight the significant role of massive activations in both LLMs and VITs. In LLMs, these activations help focus attention on specific tokens, acting as implicit bias terms. We show that introducing explicit biases can eliminate the need for these massive activations. In the context of VITs, massive activations and register tokens both serve as mechanisms to introduce biases, improving model performance. Section Summary. In this section, we explore how massive activations impact self-attention mechanisms in language models, LLMs, and vision transformers, VITs. We find that LLMs use massive activations to concentrate attention on specific tokens, introducing implicit bias terms in attention computations. Additionally, by augmenting LLMs with explicit attention biases, we can eliminate massive activations, showcasing an alternative approach to address attention biases in pre-training. In VITs, massive activations are observed in certain models like CLIP and DINOV2, serving as fixed biases that influence attention patterns, similar to the function of register tokens proposed in VITs. Section: Related work. In this section, we delve into the fascinating characteristics of autoregressive transformers, particularly focusing on the observations made with GPT-2 and other large language models, LLMs. We've noticed that in the layer just before the last one in GPT-2, there are certain dimensions of features where the activation levels can reach as high as 3000. This discovery highlights that a small number of these dimensions play a significant role in several standard methods used to evaluate how similar representations are. We also observed that the magnitude of the feature representing the initial token in GPT-2 increases at a much faster rate compared to other tokens. Furthermore, our investigations have revealed the presence of exceptionally large weights in the layer norm component of both GPT-2 and Llama 2 to 13b. When these weights are set to 0, the performance of the models drastically decreases. Interestingly, the feature dimension associated with this weight in Llama 2 to 13b, which is 2100, matches that of a very large activation. When it comes to outlier features, various studies have explored their presence in LLMs, noting that these features often have high activation values across most of their sequence dimensions. Although at first glance, massive activations might seem similar to outlier features, we've discussed their fundamental differences. More crucially, we demonstrate that massive activations cannot simply be explained by the presence of outlier features. Our research also covers attention concentration patterns, where we've found that attention in models like BERT often zeroes in on specific tokens such as the separate token, SEP. Other studies have shown that LLMs tend to give most of their attention to the first word token and have identified attention artifacts in vision transformers, VITs, including sparse activation patterns that draw attention to certain tokens. Our work goes further by providing a detailed analysis of why these patterns occur, especially in relation to massive activations. Regarding biases in the self-attention mechanism, it's clear that there are various types. For instance, simple additive bias terms can be introduced in linear layers to compute the query, key, and value states. Additionally, position biases can be incorporated into self-attention to account for the positional information of each token. There are also different versions of biases that involve manually designed softmax operators. Our findings reveal that LLMs, even those using standard self-attention, inherently introduce implicit bias components into the attention calculation through massive activations.